continuing to lecture on here. Hopefully you had a nice break. We got a little bit of chapter 2 to finish. We're going to roll into 3, then we'll roll into 10, then we're going to do 12 and 13 all today. All right, so we have a little bit of chapter 2 to go over officially here. We laid up, I think, last time talking about density. We did talk about really one of the main calculations that you need to know how to do as you go through your chemistry sort of career here at Saddleback is, again, that dimensional analysis, the way that we set up our calculations using our units and our conversion factors so that we could clearly see what units are canceling, what units we are left with. Remember, that is pretty much how they want you to set up all your calculations as you go through chemistry. We use conversion factors, which come from equalities, and from any equality, which is basically two things that represent the same amount of something, but are on different units, you could get two conversion factors for. Remember that when we do give our answer sort of in significant figures at the end there, and we're doing some type of dimensional analysis or conversions, we usually do not have to worry too much about the conversion factors as long as it's metric to metric or English to English. It is only, again, when we cross over to that English to metric sort of conversion, you should look at it. More times than not, though, probably the original number that you're converting is probably the right number of significant figures for your answer, but not 100% of the time. But you should look at, obviously, the conversion factors if you need to, especially if it's metric to English. The couple that you don't have to worry about on that is that 1 inch is 2.54 centimeters, and that 1 pound is 453.6 grams. I think we laid up there, as I mentioned, with density, so that's what we'll pick up again just to sort of officially finish out the conversation here in this chapter. Density is defined as the amount of matter there is per volume of a substance. Density, again, has basically two types of units usually. Grams per milliliter or grams per cubic centimeter. And these are really the typical units we see for solids and liquids. Remember that, again, a milliliter is the same thing as a cubic centimeter. It's basically a 1-to-1 conversion between them. Typically, when we give the density of something, that is how many grams there is per milliliter. So the number stays with the grams part is per 1 milliliter or 1 cubic centimeter. We don't really deal too much with gas density in this class, but in 1A you might. But typically gases, though, usually have units of grams per liter in terms of their density. But again, we really don't deal too much with that in this particular class. So most of the time, if you're dealing with density, those are going to be probably your two units that you see. When we look at the different densities of objects, for example, with water, that determines whether or not it will sink or float in water. So if something is more dense than water, we would expect it to sink. If it is less dense than water, then it would float. We also can look at the densities of different liquids. For example, if we threw into a container some different liquids, they would separate out into some different layers, maybe based on their density. And this bottom layer should be the most dense of all of them, while whatever the top layer, we'll call that the top layer, should be the least dense in that particular case. So if we threw something solid in there and it like stopped right about there, that would mean that it's obviously more dense than what's above it and obviously less dense than what's below it if we put something solid in there. So when we talk about density, there obviously is a formula for density, which is density is mass divided by volume. And that is obviously in a formula that you do need to know, and obviously how to properly rearrange it. So mass divided by volume. Volume would be mass divided by density, and mass would be volume times density. Sometimes people remember this with the DMV triangle here. So density is mass over volume, volume is mass over density, and mass is density times volume. You obviously need to be able to rearrange that equation and solve for any of those things. Very commonly, we solve for all three of those things: mass, density, and volume. Probably very similar to what you did there in that experiment last week. So let's try an example here. The density of a block that has a volume of 25.3 cubic centimeters and a mass of 21.7. So take a moment and calculate that. We are looking for our density, which is mass divided by volume. In this case, we do have the volume given to us, which is 25.3 cubic centimeters. We also have the mass given to us, 21.7 grams. So we're good to go to just plug in. So 21.7 grams divided by 25.3 cubic centimeters. Gonna get us a number. Gonna give us a 0.858. The units are grams per cubic centimeter. Once again here, these units do not cancel each other out. They still remain, and you should keep them. And as I mentioned earlier, the number stays with the grams part and is per 1 cubic centimeter in this case. In terms of significant figures here, we're doing 3 divided by 3, so we should end up with 3 at the back end there of our calculation. Any questions on that one there? Now, we talked a little bit about different ways you could kind of get volumes, and you did a bunch of these during the experiment probably last week. But there's really kind of 3 main ways that we could get the volume of sort of an object or a substance. We could, if it is a liquid, we could just pour it into something like a graduated cylinder, and we could take a reading. If it's some type of solid cube like you did the other week, you could take your ruler out and do some measurements of the length times the width times the height. The most common way or very common way that we get the volume of a solid, especially dealing with sort of density, is volume by displacement. And that basically means that we fill up some type of container with some liquid like we got going on here as our initial volume. When we take a solid object like so and goes in for a swim in this particular case, she is going to displace a certain volume of that liquid. The amount of volume of that liquid that she displaces is actually equal to her own volume in this case. So if we take the difference between obviously where we started and where we ended, that will give us our volume of our object in this case. And that would be our final volume minus our initial volume. So this is a very, very common way, like what you did with the stopper, the rubber stopper in the graduated cylinder, filled it up, took a reading, dropped it in, took another reading. To figure out the volume of that stopper in that particular experiment. Any questions on that there? Hopefully she could get out or hold her breath a long time. Maybe those are stairs. We don't know. Hopefully she'll survive. We'll see. All right. So let's try one here. A student fills a graduated cylinder to 25 milliliters. Then tosses a solid in there carefully. 33.9 milliliters. The volume goes. And the solid has a mass of 63.5. What is the density in this case? Okay, let's take a look. So obviously we're doing still with density here, which will be our mass divided by our volume. This is obviously a displacement type situation. So we got something like a graduated cylinder that's at 25 milliliters. Got a solid we're going to put in for a swim there. That raises the volume to 33.9 milliliters with our solid in there. So once again, the difference between these two will give us the volume of that object. So our object here will be our final volume minus our initial. So that's going to give us 33.9 milliliters minus 25 milliliters. Going to give us 8.9 milliliters. So we now have the volume. And we obviously have the mass there given to us in the problem. So we have everything we need to solve for the density. Density here would be 63.5 grams divided by 8.9 milliliters. Going to give us a 7.1 grams per milliliter. Any questions on that calculation? Yeah. It doesn't really necessarily matter in this particular case. You could leave it in either one since they're basically a one-to-one conversion. Sometimes if you were doing sort of the measurement where you use a ruler, that's usually you kind of do the per cubic centimeter. Since here we're actually using volume and a liquid here like water, we would take more to like a milliliter sort of reading. So that's why we would leave it in that. But numerically, they would be obviously equal to each other. It really matters. In this case, you would leave it as grams per milliliter because that's really where the volume measurements came from. But if you needed to convert it to the other, it'd be the same thing. But yeah, so if you were doing this problem because these units here and their volume rate are in milliliters, you really probably wouldn't want to change it to a cubic centimeter in that particular case. Other questions? Now, in terms of significant figure here, it is really the subtraction part, right? Which kind of determines where we end up. Since we did the subtraction part first, we go to decimal places, which is 1 decimal place, but that has 2 significant figures, which means when we do our final calculation of 3 significant figures divided by 2 significant figures, we end up with 2 significant figures for our answer. So again, as we talked about, you want to kind of keep track of your significant figures and all that through your calculations, and kind of your last calculation will help you determine sort of where you should end up. But you still have to keep track of everything up to that point. All right, so here's some density of some common sort of substances. You have this table in your book. The one you definitely should know is the density of water, and that is liquid water, by the way, is 1 gram per milliliter. So if you ever in any calculation really need the density of water and it's not given to you, which it oftentimes is not, it's just assumed that you kind of know that the density of water is 1 gram per milliliter. So that's like a value that you should definitely have in your head as you go through chemistry. That would mean obviously here everything below would sink. These guys up here would obviously float in that particular case. Anything with a less density than 1. You should also note that, by the way, density does change with temperature. So as the temperature changes, so does the density, even water. So liquid water at really not 4 degrees Celsius will have a different density. But in most cases, if you need it for a calculation, 1 gram per mil is pretty much what everybody uses. But you should be aware, and you'll see it in a later experiment in the semester, that based on the temperature, there will be some different density sort of values that can happen with the substance. And here's our other guys here. All right, let's try one more here. A student needs 150 cubic centimeters of salt for an experiment. The density is 2.16 grams per cubic centimeter. How many 1 pound boxes of salt do they need? A conversion that you do need to know. 1 pound is 453.6 grams. Yeah. All right, so give it a go. See what you come up with here. Okay, so we are again obviously dealing with density here, and 150 cubic centimeters is a volume. Our density here is 2.16 grams per cubic centimeter. So if we just try to check off what was given to us, we can see we are missing perhaps the mass would be a good thing to solve for. So rearranging that equation, mass would be volume times the density. When we have something like density, we can also use it as a conversion factor. So we could kind of use it as 2.16 grams per cubic centimeter. Or if we needed to do in sort of dimensional analysis, we could flip this around and sort of use it in the opposite direction. So if we take more of a dimensional analysis approach to show our work here, we will take our volume, which is 150 cubic centimeters. We will use our density just like it is written there as 2.16 grams per cubic centimeter. The cubic centimeters will cancel. That'll give us 324 grams as we multiply across. In terms of a little significant figure action, that looks like 2 sig figs. This guy looks like 3, which means perhaps this should end up as something like 320 grams of salt would be needed in this case. Yeah. Any question on the calculation there? Now, the other thing we want to also make sure that we do is answer the actual question, which is really how many 1 pound boxes do we need? And since obviously 1 pound is 453.6 grams, you would only need 1 box with some left over at that point. Yeah. Any questions on that calculation there? Question? Yeah. You should try where you can. to do it as dimensional analysis. I'll put it that way. There are going to be certain formulas where it's just like a plug and chug type into the formula. But if it's a situation where you can really show your work with dimensional analysis like we just did here, you really should kind of show it that way. That's sort of how they want you to do it. Later on, like I said, or even like in the earlier problem that we did where we have the mass and the volume, so clear that you're just going to plug and chug into there. You don't have to try to force dimensional analysis into that calculation. But something like this where you can kind of show, you probably should do it. Would I take points off? I don't know. It depends on the situation, but probably you'd be okay. But they do definitely want you wherever you can to kind of show the work that way. Other questions? Okay. All right, that wraps up chapter 2. Seems like fun. All right, it's good times. All right, we're off to chapter 3 now. Okay, so here in chapter 3, we're going to talk about matter. We're going to talk about different states of matter. We'll also talk about substances, elements, compounds, mixtures, and how to separate out mixtures, which will work pretty good for your lab today, I think. So we talked a little bit about matter, maybe at the very beginning of class, but this is officially the chapter of where you can find it. Matter, again, is basically the stuff that the universe is composed of. It does have mass and occupies space, which is pretty much everything. There are 3 states of matter as we've gone through, but again, just to reiterate, we obviously have the solid state of matter where things are packed in really tight to one another. Things have definite shape. They're very difficult to change the shape of it. Obviously, like this wall, right? Pretty solid. Not that easy to sort of change the shape of it. We also have liquid state where things are still in there relatively tight to one another, but there's a little bit more room for movement. There's a little bit more energy, which allows those guys to sort of pass one another. And again, that's why when we think about liquids, they are sort of fluids, things like water, gas. Liquids have a definite, do not have a definite shape, but they do have a definite volume. So what that means is if I take 10 milliliters of water and I put it in the trash can, it should take the shape of the trash can. I put it in the water bottle, it should take the shape of the water bottle. I put that into like a silly straw, right? It should take the shape of the silly straw. A definite volume means that if I started with 10 milliliters and all I did was move it from one container to the next, and I'm not like a klutz and spill it, I should still have 10 milliliters, no matter sort of where I put it into as I go through it. The last state of matter is gas. And obviously in the gas state of matter, everybody has basically broken apart from one another and they're flying around, as we'll talk about in the gas chapter again. That is what we associate pressure with. Because they are constantly flying, they have a lot of energy. They usually will fill the container they're in sort of uniformly. So they really sort of take the shape of the container because they're thought of as flying around. As we'll talk about when we get to gases, one of the things that makes something, for example, what's referred to as an ideal gas is the idea that we really look at the volume of the container the gas is in, because we assume that it is sort of flying around the entire container completely rather than the volume of the gas itself. So if a gas is in like a 250 milliliter container, we think the gas is 250 milliliters, even though the gas itself may not actually be that volume because it will fill the container sort of uniformly. I think we also touched upon earlier on as well, but just to review here, as we go from one state to the next, as we go from solid to liquid, that again is the process of melting. As we go from liquid back to solid, that is freezing. Taking our liquid to our gas, that is evaporation or vaporization. Condensation is occurring as we go from gas back to liquid. Solid skipping, again, our liquid part is our sublimation. And really gas skipping liquid is known as deposition. So again, these are what are referred to as sort of the transitions or phase changes that occur. And a lot of it involves energy sort of component to it. And as we go from, again, solid to liquid to gas, those are all processes that require energy to be absorbed. And that is endothermic type of situation. And going in the opposite direction, gas to liquid to solid, those are all what are referred to as exothermic sort of processes. Energy is released. So again, if you think about gas molecules flying around and it loses energy, not going to be able to fly around as fast, which means they're going to come in contact with each other. They also are not going to have enough energy really to escape one another. So they'll kind of stick and go into the liquid phase. And again, as you continue to remove energy in that case, in the liquid phase, they'll lose the ability to sort of pass each other and they'll kind of lock into place in terms of the solid state. Obviously, the opposite is true as you go from solid, everybody's together. As you put energy in, it gains energy. They get enough energy to start moving past each other into the liquid phase. And as they continue to gain that energy, they get enough energy to completely sort of escape each other into the gas phase. Any questions on that there? Yeah. Here's our liquid in our different sort of shapes there. Now, water is a little bit different than some substances. And one of the major differences of water is it's one of the few substances where the density of it in its solid phase is actually less than it is in its liquid phase. And we know that when we put ice in our drink, right, it ends up floating on top, right? And that's because ice is less dense than liquid water. And that's very unusual for a substance. Usually it's the opposite way around. Usually the solid state is more dense than the liquid state. And the real reason for that is as water comes together in the solid state, because of the really strong hydrogen bonding that occurs, as you can see in this picture here, it creates a lot of really empty space between all of the water molecules as they come together. So as they come together in that solid state, it's creating this really bunch of empty spots there. And we think about the density equation we just looked at. Density is mass per volume. So with all that extra empty space between the molecules, it really increases the volume. So that means the bottom number is going to be larger. And that means that the density number will actually be smaller in the solid form than in the liquid form. As you can see in the liquid form for water, not as much empty space between all the molecules, which means its volume is not going to be as large as it is in the solid state. So very unusual sort of situation for water, and it's because of the really strong hydrogen bonding that occurs between different water molecules, which is the bonding that holds them together. As they really sort of lose energy and come together, they sort of keep a pretty good distance between them, and it creates a much larger volume for ice than it does in liquid water. Any questions on that there? So again, as we talked about, it is the forces among molecules that kind of really determine, sort of what state you would see. There are some forces that also are important, things like melting points and boiling points where things sort of transition. So typically speaking, the stronger the attractive force between a molecule and itself, another molecule of the same type, the higher you will see things like boiling points be and melting points, because the stronger that those molecules can stay together, the more energy you have to put in there to get them to break apart, which requires a higher sort of boiling point or melting point. A much weaker attraction between molecules results in a lot of times a much lower boiling point or melting point. So for example, if you take something like water, it has a pretty strong attraction between water molecules and water molecules, which is hydrogen bonding, which is why it has like a boiling point of 100 degrees Celsius. If you take something like methane, which is like the gas that comes out when you light your Bunsen burner, it's obviously in the gas phase right out of the box. And that's because methane is nonpolar and it's held together with other methane molecules by very, very weak intermolecular forces, or forces that hold each of those things together, which means it doesn't take a lot for them to basically break apart. So at a much lower temperature, they're more likely to be gases. So here's our summary of what we just talked about there. Our solid being rigid, fixed shape and volume. Our liquid having a definite volume, but takes the shape of the container, bless you, and no fixed volume or shape for our gas, but will take the shape and volume of the container. Now let's talk a little bit about physical and chemical properties and really physical and chemical changes. So a physical property is one that can be measured without changing the composition of a substance. So typical physical properties of things are odor, color, volume. Most commonly we come across a lot is the state of a substance. Is it in the solid state, the liquid state, the gas state? Things like density is also a physical property. Melting and boiling points are physical properties. Physical properties oftentimes go with physical changes. And when we have a physical change, what we start with and end with is fundamentally the same substance or same thing, however you want to word it. So when something goes through a physical change, what you start with and what you end with is really the exact same thing. It may look a little different, but it is still fundamentally the same thing. So a very simple example is if you had a peanut and you crushed the peanut, it's still a peanut, right? It's just in a million pieces, or how bad you crushed it. It's still fundamentally still a peanut in both situations. It may look different. If you had a shirt that had a lot of wrinkles in it and you ironed it, it's still a shirt with less wrinkles, but fundamentally it's still a shirt. So whenever we start with something and we do something to it and it's still really the same thing, it hasn't changed into anything new, that's a physical change. So for example, when I take liquid water and I heat it and it starts to boil and create steam, is that a physical change? It is a physical change because liquid water is H2O, right? And steam is H2O. They are the same thing. Same thing if I started with the ice cube, which is still H2O, right? And I let it melt to liquid water and I take the liquid water and heat it. All three of those things, as you go from solid liquid to gas, which is a change of phase, right? Those are all physical changes because they're all fundamentally still the same thing. So in a physical change, start with, end with, still the same thing. Nothing new has formed as a result of that, which is what this example just talked about is our ice there. And again, that happens at our, say, melting point and also our boiling point when things go from one thing to the next, which are physical properties as well. Now, different to that is a chemical property or a chemical change. And really a chemical property of a substance is sort of its ability to go through a chemical reaction or even resist a chemical change or a chemical reaction to take place. Now, in a chemical change, the major difference is, as it says here, in a chemical change, what we start with and what we end with are fundamentally different things. So we've actually made something new was created that is different than what we started with. And there's really no way to get back sort of our original substance by any type of physical means, boil it, freeze it, whatever you want to do to it. You can't get back what you sort of originally started with. So for example, if we wanted to make rust, before we do that, we basically just need some iron metal and a little bit of oxygen and some moisture. And basically what will happen is these two guys will come together and basically make rust there, which is the iron and the oxygen coming together and now connected. And if you take something that's rusty or a rusty piece of metal, you could do whatever you want to it. You could heat it up, you could put it in the freezer. You're never going to get that piece of iron back by itself. You won't get the obviously oxygen back. So there was really a chemical change that occurred. Most of the time, a chemical change is a result of a chemical reaction happening. So chemical reactions are chemical changes. So whenever you have a chemical reaction that occurs, that is a chemical change. Same thing here, if I took something like water, you can run an electrical current through water and you could generate some oxygen gas and hydrogen gas, and that would be a chemical change. You can't, just put it back together physically and get the water back. You actually have to do another chemical reaction to generate the water. So that is a chemical change that will occur. What we start with and what we end with are fundamentally different things. So obviously rusting on our cars when we eat food is another example, right? Obviously when we eat food, it goes through our digestion process there. All of our food gets obviously broken down in our body to many different things and goes through many sort of chemical sort of changes that occurs. Also, for example, if you had a fire and you made a fire, right, all that wood, it gets burnt into ash and stuff like that, you can't get the wood back at that point. It's fundamentally changed into something very different along the way. We made a hard-boiled egg, same idea. All those proteins and stuff, and then the egg changed through that heating process. And obviously, again, if we eat it, it will go through another change. So when we talk about physical changes, it involves one or more changes to a physical property, but fundamentally it is still the same thing, which is really the important part of it. So for example, you take a wire and you put it into a fire, and then you take it out of the fire. While it's in the fire, it may be glowing and stuff like that, right? But when you take it out of the fire, it goes back to like exactly how it was at the beginning, right? That would be like a physical change. Maybe you'll do that later, I don't know, or something like that. So that's what you're looking for. You're looking for something, that really doesn't change too much. What you start with and what you end with, again, just some type of physical aspect of it. Mostly common in chemistry is that physical change when we take things from solid to liquid to gas and back and forth. Chemical changes always involve some type of fundamental change, which is a chemical reaction. So something like silver, for example, when it goes through tarnishing, when metals oxidize, it's also a chemical change that's occurring. It's actually a type of reaction that's occurring, which is a redox reaction, electrons being transferred. So how do we know if a chemical reaction took place? There's usually signs that we can see that a chemical reaction took place. There's really kind of few things that happen during a chemical reaction. Maybe you see a solid that was formed that wasn't there before. You see bubbles that start to happen. When we see bubbles, that's a result of what has been formed. What makes the bubbles? Gas makes the bubbles, by the way. Yes. So you'll see that today perhaps as well when you do the experiment. So when you see bubbles that start to form, that's a generation of a gas. So for example, if you took, a liquid like hydrochloric acid and maybe a solid like zinc and you threw it together, before you did that, you had no gas, right? Then obviously when they came together, you start to see some bubbles forming and gas generating, which would imply a new species was formed, right, from where you started with. So you changed it to fundamentally something different, and that would be an example of a chemical change. Any questions on physical changes versus chemical changes? All right, so let's talk a little about elements and compounds. An element really is as far as you could go back in terms of substances. Obviously, we have elements on the periodic table. Elements, again, are kind of like the alphabet. Different sort of letters coming together gives different words. Different combinations of elements will give different compounds that are formed. Elements are really made up of a certain kind of atom. So if you have a pure sample of aluminum, you should have only aluminum atoms in there. Nothing else should be there, which would make it an element. A reminder that there are some elements that do come as molecules. So we do have things like H2, O2, N2, F2, Cl2, Br2, I2. So all these guys are what are referred to as being diatomic molecules. And they are molecules because, again, the basic definition of a molecule is just that. You have two or more atoms together. So those could be two or more atoms of the same element. They could be two or more atoms of different elements. But the basic definition of a molecule is you have two or more atoms together. And in the case of hydrogen, that is what you got going on. In the case of oxygen, you got something that looks like this. Nitrogen, something like this. So those are all molecules because they basically contain two atoms of each of those elements. They are still considered elements because something like H2 only contains hydrogen atoms, so it is all the same element involved. So these are also elements as well. These are naturally how they all come, right? By the way, everybody else on the periodic table comes as monoatomic atoms. Mono meaning one, so they come as ones. By the way, as well, things on the periodic table, if you just have those elements by themselves, do they have charges? Like sodium, magnesium, do they have charges? They actually don't. So things do not have charges until they sort of combine with something else. So for example, metals don't get charges until they combine with non-metals. That's how they both actually get charges. So things like that we have written up here, which are all non-metals, they don't have charges either. And things don't get charges until they really combine to form like an ionic compound. By themselves, so you take a piece of zinc metal like you're going to do today, technically that zinc metal has no charge and doesn't have a charge until it reacts. When it reacts, now it will have a charge. But before it reacts, it has no charge or anything like that. Any questions on that there? Now, a compound, we might have touched upon as well, but a compound is a combination of two or more atoms of different elements. So that's the important part there. In order for it to be a compound, you have to have two or more different elements involved. So atoms of two or more different elements involved. So for example, water, which is H2O, basically our water looks something like this. This is a compound because it has two or more atoms of different elements. Water is also a molecule because it has two or more atoms together. Water is an element. No, water is not an element, right? So water is not an element because it obviously has hydrogen and oxygen, which are two different elements together. So water is a compound and a molecule, just like H2. H2 is an element because it's made up of just hydrogen. It is a molecule because it has two or more atoms together. Is H2 a compound? H2 is not a compound because it has only hydrogen atoms together. So it would need some other element to become a compound. Any questions on the difference between those things? So unlike elements, which are really as far back as you could go, compounds can be broken down into simpler things like their elements by some type of chemical reaction. So like the example that we just looked at there, we took our water once again and run an electrical current across it. You can break it down into its elements. So we could take our compound to its elements by running an electrical current over it. I don't know if we're doing it anymore, but we used to do it in this class. You take like a 9-volt battery, some water, and hook it up, and you could basically break apart water. You cannot go any further than elements. So once you hit the elements, that's again as far back as you can go. A compound always contains different elements. So like water is H2O, carbon dioxide is CO2. Now, the properties of compounds are usually very different than the properties of the sort of elements that make them up. So, for example, liquid water has very, very different properties than hydrogen gas and oxygen gas. Hydrogen gas, oxygen gas, kind of explosive. Water, not so much, right? We also maybe know something like salt, like a sodium chloride or something, right? That has very different properties than sodium metal, which is a soft sort of gray metal, and chlorine gas, which is a toxic green gas. But through the miracle of chemistry, when they come together, you could throw some of that on your fries and not die and stuff like that. So obviously salt has a very, very different property than the two elements that make them up. And that's very common. Usually the elements that make up a compound, for example, very different sort of properties than when they do come together in that sort of compound form. Any questions on that there? So then let's talk a little bit then about mixtures and pure substances. A substance or a pure substance is any form of that matter that has a definite or constant composition. Water, ammonia, sugar, for example. They also have very unique sort of properties. So if you had water versus ammonia, you could definitely tell the difference by the smell. Ammonia definitely smells much, much different than water. Substances differ from one another and by their appearance. Obviously, sugar looks different than gold, and that looks different than water. Now, a mixture is when you take two or more pure substances and put them together. So, for example, if we had water by itself That is a pure substance. If I took some sodium chloride or salt, that is a pure substance. If I throw both of those guys together, I basically make salt water, right? Our sodium chloride here, solution. AQ is aqueous, means a water environment. And salt water is a mixture. So we basically took both of those pure substances and put it together. One of the most important things about a mixture is when we put those things together, everybody still retains their identity. So even though it may not look like something's there, everybody still is able to actually maintain their identity. That's really important because when I make a mixture, would that be a physical change or a chemical change that everybody maintains their identity? It's a physical change, right? Because although it may not look like it, everybody's still there in their original form, believe it or not. Even though with salt water, when we look at salt water, it just looks like water. You can't really see the salt, right? Unless you taste it. The salt's actually still there. You just can't see it because it's wrapped around a bunch of water molecules are basically surrounding it. So when we dissolve something like sodium chloride, what happens is the sodium ion, which is positively charged, and the chloride ion, which is negatively charged, they actually get surrounded by water. Water actually has two parts to it. It has a positive side and it has a negative side, which is why water is considered to be polar. And opposites attract. So what happens when you put like an ionic compound like sodium chloride in water is the negative side of water, which is the oxygen, will surround the positive ion there. And the positive side of water, which is the hydrogen, will surround our negative guy here. And that does really two things. That's really how something dissolves, is basically all those ions get surrounded by the water. It also prevents those ions from coming together to make a solid. And it will also mean that we can't see it anymore because what happens is there's a ton of water molecules, a lot of water molecules when you go to dissolve something. So all those ions get trapped in the water matrix and it's no longer visible to us that the salt is still there. So it looks like it maybe disappeared. And that's why sometimes people, when they go to dissolve something like that and make a solution, they think that maybe a chemical reaction or chemical changes happen because you can't see the salt anymore. But it is actually still there. It just gets wrapped up with a lot of water, so you can't really see it. There are different types of mixtures that we come across. One is a homogeneous mixture. In a homogeneous mixture with sufficient mixing, everything will look the same throughout. So with a homogeneous mixture, those things are usually called solutions, and those are all the things that you see that has the aqueous symbol next to it are really solutions. So salt water is an example of a homogeneous mixture. Again, if you put the salt into the water, it will dissolve. It won't look like there's salt in there. Same thing if you took some sugar or something like that and put it into the water, the sugar would have no trouble dissolving. So that is definitely a homogeneous type of mixture. The other type of mixture is a heterogeneous mixture. And in a heterogeneous mixture, even with sufficient mixing, you will still see different phases, as sometimes referred to, or different layers. You'll still see the things. So, for example, if you took some sand and you put it in water, like you'll do today, you can mix that thing all day. It will never dissolve the sand. You will still see the sand in the water mixture there. Also, if you took some metal pieces and you put metal into the sand and mixed it all day, that solid metal is never going to sort of go away or dissolve or anything like that. If you take a chocolate chip cookie, you still see the chocolate chips, right, in that mixture of all the other stuff in the cookie. And that's a heterogeneous type of mixture. Now, regardless of the type of mixture that you got going on, homogeneous or heterogeneous, you can separate them back out by some type of physical means. So even though you have a mixture that you may look at and go, I don't know how you would separate that out, you can still separate out that mixture back into its original components by some type of physical means, which means you can physically separate them, you could heat them, you could boil them, you could do something to them to sort of separate them out. So for example, if we look at the sand and water example, that is again a heterogeneous mixture. And the best way usually to sort of separate out a solid from a liquid is the process known as filtration. And in filtration, you usually take a funnel, you put a piece of filter paper in there. And if you take your water with your sand in there and you dump it in there, what's going to happen is the liquid water there will have no trouble. It will pass right through, and all of your sand will be caught on your filter paper there. And through this very simple physical sort of separation process of filtration, you've now separated back out the two components of this mixture, both the water and the sand. You can let the sand dry out and it'll be just like it was originally. And you obviously have the water like it was originally. So again, here in that mixture, you could definitely separate out each of those components. Now, you could also do a separation that involves something that's a homogeneous mixture, like say our salt water. And if I set up an apparatus such as this, a word linearly drawn here, and we put our salt water on one side, this is all a closed sort of environment. And we have this sort of tube that connects each side. If we keep this tube really cold, this is going to help us out as we try to separate out our salt water. Our salt water, which is obviously a homogeneous mixture. As when you look at it, again, you can't see the different components that are involved. If we take this apparatus, which is an enclosed sort of apparatus with our salt water, and we start to heat it, as I start to heat the salt water, what's going to happen to the water part? Yeah, it's going to start to evaporate, right? So that means that the steam is going to start to evaporate off the water, and it's got really nowhere to go but down this tube. So now I have basically gas that goes down a really cold tube. It's going to go through condensation. Yeah. And as it does so, what's going to happen is you will now get the water, right, to sort of drip out on the other side. If you continue to heat this, at some point, you will evaporate off all of your water. And you will be left with just the salt on the other side, no more water. And you will have basically a residue of salt on this side. So by doing this very simple procedure, we've now separated out this saltwater mixture where you couldn't really see both components, but now I can see the water component by itself. I have the salt component over here that can dry out, and I have now successfully separated out my homogeneous type of mixture along the way. What was that? Was it? Oh, I was wondering if somebody kicked something. We'll hope it's just like a small little injury. He'll fly away. All right. All right. So when we have this type of separation here, what we're really doing is, if you go back to sort of what we were looking at with our sodium and our chloride here, where it is surrounded by those water molecules. Those water molecules, as it's in solution, does a really good job of keeping each of these ions basically apart from one another, because without it, those ions are really, really attracted to one another. So they would want to come back together. So in the liquid sort of our aqueous solution form, where we started with on this side, as we heat it and we get rid of these water molecules, there's now really nothing to prevent these ions from coming back together. And that's why you see sort of the solid reappear that wasn't there before, when we get the water pretty much out of the way by evaporating it off. This is a process known as distillation. And what we're really doing here is taking advantage of the physical properties of each of these substances. So the physical property of water and also the physical property of sodium chloride. Water has a lower boiling point than sodium chloride because sodium chloride is actually held together by electrostatic attraction, which is an intramolecular force. And you could take a ionic solid like sodium chloride and you could heat the crap out of it and it will never go into the gas phase. It will just start melting before it does so. It's held together so strongly. Now, water, on the other hand, we know we just simply need to get it up to 100 degrees Celsius, right? And it will start to boil. So by knowing that sort of difference between those two, we could very simply heat that solution and taking advantage of the differences in their physical boiling points. We can allow the water to come off first, and we know that the salt's going to hang around because it's not going to get anywhere near hot enough for that thing to get into the gas phase. So we're actually taking advantage of physical properties of each of these substances to allow us to separate it out in that process of distillation. Any questions on that there? Here's a much prettier picture. I know mine was award-winning, but this is really a much better picture of what you're looking at. So this is a distillation apparatus, expensive, but here's our salt water. And again, as you heat it, it's got nowhere to go. It's going to come down our tube here and come out until we have really our salt left. You're basically today going to do a version of this without the saving the water part. So what you're going to do is you're going to basically have a mixture of salt, sand, and water, right? Which is really a heterogeneous mixture because you can see the sand and the salt water together, right? You have a homogeneous mixture of just the salt water, but when you add the sand into it, you have the heterogeneous mixture. So what you're going to do is you're going to filter that thing, right? And that's going to leave your sand on your filter paper. You will then have your salt water left over. You're going to take your evaporating dish and basically put your salt water in there. And then you're going to heat it up. And when we heat it up on our evaporating dish, you're going to put your little watch glass on there. We're not worried about the water. Water is going to be separated out. It's just going to go out into the air, right? As it comes out as steam. So we're not going to really collect the water. But what should be left in your evaporating dish at the end, right, is your salt that would be left over. In the second experiment, you'll have some zinc chloride left over there in there. So same idea here. So again, you were going to take advantage of the differences in physical properties to allow you to separate out those three mixtures, one by doing a filtration and one by doing really sort of a difference in boiling point sort of properties. Any questions on any of that there? All right, that is chapter 3. That's a fun chapter. We're rolling. You thought I was kidding when I said we're getting to like 13 today. No, I'm just kidding. All right, we are off to chapter 10 next, believe it. So we are off to chapter 10 here. So we are going to go ahead a little bit to chapter 10, and then we'll come back. So in chapter 10, they assume that you probably did all the other chapters in between. So there might be some conversation about reactions and stuff that they kind of assume you've already covered, which we obviously didn't. So we'll cover some of those things. But in chapter 10, we're going to talk about energy. And this should be, believe it or not, the last chapter I think we got rolling before our first exam. Yeah, so this should be the last chapter. We do have a quiz on Monday. Yes, right. On chapters 1 and 2 at the beginning of lecture. Yeah. So here is energy. So let's talk a little bit about energy. When we talk about energy, we think about energy and the idea of the law of conservation of energy. And we think of energy a lot of times in chemistry as sort of this nice, perfect transfer of energy from one place to the next. We neither create nor destroy energy along the way. So when we think about energy moving, the idea is pretty simple of if somebody loses a certain amount of energy, somebody else will have to pick up basically the same amount of energy. So when we talk about things, there's really two types of things. There's like the system, and the system is pretty much whatever you're sort of dealing with. So if you're doing some reactions in a beaker or something like that, then that's your system. And then pretty much everything outside of that is the surroundings. So we have our surroundings outside of that. And when we think about energy flowing, for example, if the system lost, say, 150 kilojoules of energy, it would be negative for the system is because it's exothermic. So typically in energy, when we calculate values of energy and we see a negative value for energy, that means that it's an exothermic process and energy is being released. what we would expect to happen in this situation is the surroundings would actually pick up positive 150 kilojoules. It will actually pick up the exact same amount of energy that was lost by the system. It's positive for the surroundings in this example because it's endothermic for the surroundings. It's basically picking up all that energy that's being released by the system. So in chemistry and in general for energy, when we calculate energy values and they end up being positive values, those are usually endothermic type processes. And that means we are absorbing energy. And if we calculate any type of energy value, or you see an energy value that is negative, that is a exothermic process. And that usually means that is a process where energy is being released in this particular case. So when we talk about systems, there's usually a few different types of systems that we come across. In most cases, the first and the second one there is very common. What we do use an open system or a closed system, or we can have an isolated system. In an open system, we can have an exchange of mass and also energy with the surroundings. In a closed system, we sort of eliminate the mass leaving that process. So we have only the exchange of energy that's happening. And in an isolated system, we have basically no exchange of mass or energy. So here's some examples of that. Like if you have a flask that's open, you could definitely go in and take out stuff. You also have the exchange of heat happening. If you throw a stopper up there on the flask, that's going to prevent anything from leaving or entering. But we could still have, obviously, the exchange of heat. And if you have an isolated system, you have really no exchange of mass or heat. For example, sometimes an isolated system is a calorimeter, sometimes referred to as a bomb calorimeter. They sometimes use that to figure out the caloric value of food. They put basically the food item in a isolated sort of chamber, has water in it, and they basically set it on fire. And as it's burning in there, they basically can figure out through a calculation of the change in the temperature of the water, how much energy or calories, nutritional calories, basically came off of your food by the change in the water. They use an isolated system because they don't want the outside, right, influencing the temperature of the water. And they don't want anything obviously coming in or out that would influence the temperature of the water. So in a very isolated way, they know that all the change in temperature to that water was a result of that, say, food burning, basically, in that situation. We also know, if you hold a test tube, right, you can sometimes feel it get hot or cold, right? So definitely that exchange of heat and energy can happen in a test tube, which can be either an open or a closed system, depending if you put a stopper on it or not. Now, when we talk about energy, as I mentioned, it is the capacity to do some type of work or produce some type of change. Very common units of energy that we come across a lot in chemistry. I would say probably the most common units of energy is a joule or a kilojoule. And the relationship there is 1,000 joules is equal to 1 kilojoule. So those are definitely units of energy that we see a lot. I would say second to that is calories, and that's lowercase c. And kilocalories are also very common units, and it's the same sort of conversion. 1,000 calories is 1 kilocalorie. By the way, a nutritional calorie is a capital C, yes, and that's actually 1,000 of the little calories with a little c, and that's the same thing as 1 kilocalorie. Yeah, so that is the relationship sort of between those. There is a relationship between joules and calories in terms of how you calculate it, and we'll talk about it a little later in this chapter here. There are different types of energy. So there are chemical energy. For example, there's energy stored within bonds in a chemical reaction, and there's a certain amount of energy required to break bonds and make bonds in that process. So for example, if I had a bond that was made and I wanted to break it, do I need to put energy in or take energy out to break that bond? energy actually needs to go in. So when these guys gain energy, they have enough energy, they wiggle away from each other and they break apart. So actually, when you break bonds, it's an endothermic process. Energy has to be put in there. Everybody gains enough energy to sort of wiggle away from each other. When you want to actually make bonds, you got everybody kind of wiggling. So they actually have to release energy, exothermic. And as they do, they kind of slow down and they're able to sort of come together to make that bond. So actually making bonds is an exothermic process where energy is released. There's other types of energy that you might be familiar with. The classic potential energy, which is the energy associated with the position. Every textbook has the classic example, the giant boulder on top of the hill that's about ready to fall, and it has a certain amount of potential energy based on its position. Obviously, when it goes over the hill here, it can transfer itself to kinetic energy, which is the energy of motion. And eventually, right, the rock will hit the ground and it will actually transfer all its energy to the ground. It will end up at a different level of potential energy once it hits the ground. But the law of conservation of energy is that idea that energy can be transferred from one place to the next, but we don't really create nor destroy energy. So that big giant boulder with all its energy as it's moving transfers that energy to kinetic energy. And again, when it hits again, transfers the energy to, say, the ground, hopefully nobody underneath it as it does so. There's also another type of energy, which is known as thermal energy. And thermal energy is the energy due to the random motion of molecules. So the more molecules and atoms that you have, there's going to be a greater amount of motion sort of happening and a greater thermal energy. And sometimes people misunderstand or confuse thermal energy and temperature. There is a difference between temperature and thermal energy. Temperature is really the measure of sort of the energy of a substance, while thermal energy is really related to how many molecules you have. So a sort of example difference between the two is if you have like a bathtub full of water, or you have like a coffee cup full of hot water, right? So maybe the bathtub's 40 degrees, maybe the coffee cup full of the hot water is 90 degrees. The one that actually has more thermal energy is the bathtub. As the bathtub has a lot more molecules in it, a lot more motion, and that's going to happen. The coffee cup, although it has a higher temperature because there's a smaller volume of water in there, right? So because of that smaller volume, it takes less energy to increase the temperature of it, so it can get much hotter. If you try to heat up a bathtub of water, it's going to take you a while to change the temperature because water has a specific heat capacity of 4.184, so it takes a lot of energy just to change it by 1 degree Celsius. So temperature is a reflection of the amount of energy that's happening in that particular sort of area based on how much is there. Is not necessarily the same thing as thermal energy. So something could have a lower temperature, but a much higher thermal energy because there's a lot more molecules than something that is much smaller that could have a higher temperature, but less thermal energy because there's less molecules that are involved.